Hello everybody, welcome back to another glorious maths video. Today I'm just going to be proving a couple of things about short exact sequences, and one really cool lemma called the Snek lemma about long exact sequences, which I think probably comes up in homological algebra somewhere, because I know that exact sequences appear quite a lot in homological algebra, well they appear quite a lot everywhere, so it's quite important to know this stuff in general. Yeah, because why not? And this is a new series called Because Why Not, where I just do random maths and I might put chess things in here. I might prove the hairy ball theorem in here. Yeah, just anything really. Okay. If you guys have any problems for me that you want to put down in the comments, then I might just dump the solution in this series. But okay. Right. So first, I'll just define an exact sequence. So if we have a sequence of homomorphisms, so say we have let's call it G, I. Let's say we have group homomorphisms, or let's just say we have module homomorphisms here. And this goes via Fi to Gi plus 1, and then this goes via Fi plus 1 to G 2, and so on. This is exact if the image of Fi is the kernel of Fi sub 1. Oh, sorry, the image, not the kernel. The image of F sub I is equal to the kernel of F sub I plus 1. Okay, this is the definition of an exact sequence. Okay, so what a short exact sequence is an exact sequence of the form, so we'll just call it a SES. Short exact sequence. Okay, is an exact sequence of the form, takes you from the 0, and then this goes via the 0 homomorphism. This arrow is here is unique to G prime, and then this will take you via F, and F is injective, I'll prove that very quickly, to G, and then this goes here to G double prime. And then via the 0 homomorphism here. And G is surjective. Okay, so here, this is the 0 homomorphism. And the image of this is the kernel of this. Therefore, the kernel of F equals 0, which happens if and only if F is injective. And the kernel of the 0 homomorphism is G double prime. And this will only happen when G is surjective. Surjective. Okay? So yeah, these are two pretty important facts, which are just, good to know. Okay. Now, I'll prove the first isomorphism theorem, which is quite important because it gives us a nice little corollary which relates these short exact sequences with quotient groups. Okay, so the first isomorphism theorem. Okay, and what it says is, given a surjective group homomorphism F, which takes you from G into H. Okay, if we put K equal to the kernel of F, then this homomorphism, which takes from F prime, called F prime, which takes from G mod K into H, is an isomorphism. Okay? And the proof, okay, is, yeah, it takes from G. Yeah. Okay, and the proof is, and it's well defined. It's well defined. I also have to prove this well defined. Well, okay, because and it's also defined as F prime of gk is equal to f of g. Okay. So this is well defined in an isomorphism. This is what the theorem claims. And to do this, well, we've already gotten that this is a surjective homomorphism. We just have to prove there's injective to prove there's an isomorphism. So, to do this, we'll let f prime of gk equal f prime of g prime k. Now, what this implies is that f of g equals f of g prime, and to prove injectivity we have to prove g equals g prime. Okay, so to do this, this implies, okay, so this means that the identity on h is equal to f of g inverse times f of g prime. And this is equal to, well, remember by the properties of homomorphisms which I proved somewhere, maybe 1.2, I'm not sure if that's where I did Cayley tables, but somewhere in my abstract algebra series, I proved that f of g inverse is equal to f of g inverse for a group homomorphism. Okay, so this equals f of g inverse times f of g prime, but because it's a group homomorphism, we can just do this. Okay, so hopefully that makes sense. And then this implies that g inverse g prime is in k, or in other words, that g prime is in the same coset as g, so we can just say that g prime equals g. And to prove that it's well defined, well, we'll have f prime of gk equal to f of g f of k, and this is the kernel, so this is equal to f of g times e, which is equal to f of g. So it's well defined. Okay, so that was quite a nice theorem. And why did we prove it? Well, we can see we have quotient groups, we have kernels, we have surjective. This has got to have something in relation to these short exact sequences, right? Yes, your intuition is correct. The corollary is that the following diagram commutes. So if we have a short exact sequence, and then underneath we have another short exact sequence, so all of the rows are exact. Okay, so the rows are exact. H is the kernel of H is the kernel of G. Okay, and now these vertical maps here are isomorphisms. Okay, and this commutes. Okay, so this is a nice little corollary linking these short exact sequences. They're same as this short exact sequence here with this quotient group here up to an isomorphism. Okay. Now we move on to long exact sequences. It doesn't look cool at first, but trust me, it will end up being cool. So consider just a commutative diagram. So we have 0, mapping to A, mapping to B, mapping to C. And this goes via F, via G. Then we have A prime, mapping via F prime to B prime. And then this maps via G prime to C prime. And then this maps to 0. And then we have these arrows here, A, B, C. So we have this commutative diagram. The rows are exact. Exact. And the diagram commutes. Okay, so this diagram commutes and the rows are exact. Now, what the Snek lemma says is that we have an exact sequence of co-kernels and kernels. Coca. So yeah, we have a sequence of, we have an exact sequence. Okay, we have, okay, so it takes you from the kernel of A to the kernel of B. Actually, I'm going to do these arrows in black. To the kernel of B, and then this takes you to, there's some black pen, red pen level stuff here, to the kernel of C, and then this takes you here. Now this arrow here is important, I'll actually call it D, and this takes you to the co-kernel of A. So coca, that's just a funny word, of A, and then this takes you to the co-kernel of B, and then this takes you to co-kernel B, and then this takes you to the co-kernel of C. Okay, and the reason I'm doing these arrows in black is because now I want to expand out this diagram, and it's gonna look absolutely amazing. So on top, okay, so this is the explanation of the name. Why Snek? Lemma. Okay, and when we expand this out, so we'll have the kernel of A, and then, okay, we'll just do the middle here. So we have zeros going here, and then this will go to A, and then don't forget our origin diagram. This will go via A to A prime, and then this goes via F prime to B prime, and then this goes via G prime to C prime, and then this goes to 0, and then this goes via F to B, and this goes via G to C, and we have these arrows here in the middle. Okay, now you'll see the name coming into action here. We have going to the kernel of B, and then this goes to the kernel of C. Okay, nothing too new here. But now it gets super exciting. And we'll have arrows here, actually. I'll just draw them in. Kernel C. But now, here's where the name comes into action. We have a little S shape all the way. So this is like the snake coming all the way down to the co-kernel of A, and I just want to appreciate this snake. That is amazing. And then this goes to the co-kernel of B, and then this goes to the co-kernel C. I mean, just look at that. That is awesome. And this is the expanded diagram. Adding some arrows which takes you from here to here. I know that not labeling them will imply that they're unique, but yeah, okay. They're not unique. I don't think they're unique. Okay, and yeah, this is just a beautiful, long, exact sequence. Just this snake going all the way down to the co-kernel of A. And, okay. Actually, the proof is quite long, so I just want to leave this on my board. So, you know, I'll sleep well tonight just looking at this. It's just, I love how it just snakes downwards. It just, yeah, it's amazing. But, okay. I think this is enough. You just have to trust me. I just wanted to include this because I wanted to do something about long exact sequences. And I just wanted to include this diagram as well, so it worked out perfectly. I might do a video on homological algebra, either in algebraic topology 3.1 or something, or maybe I'll just dump it in this series, like hour-long video on homological algebra, because why not? But yeah, this is really cool. Also, speaking of long exact sequences, I might prove some Mayer-Torres long exact sequences in here, or in K-theory 1.4, and or in algebraic topology, or maybe all of those, but yeah. But I think next in this series we'll be proving the Hairy-Ball theorem. But yeah, this is some cool stuff. So this is just awesome. This is pretty cool. This is pretty cool. But I mean, I don't want to be biased, but this is some of the nicest stuff I've seen in a while. Anyway, yeah, I guess I'll see you in the next video. Bye.